Hello, mother lovers. It's time for stats. October 2020's first. Let's go. Number one, then, we have some probability stuff. Looking at question A, then, write down any pair of mutually exclusive events. What that tells us is that they both can happen at the same time. So if we took two events, A and B, and we thought about their intersection, the probability of that thing should be 0. What that means for our diagram, when we look at the two circles, or any of the circles, they shouldn't have any overlaps, any intersection points. So we can see A and C would be good, yeah? A and C. You can get D and C as well. They don't cross over. So we'll call that C and D. And then we're also going to get B and D. No intersection between those as well. So B and D. Any of those will get some marks. Give them a circle. Big tick. And I move on. Next one then. We're told that the probability of B is 0.4. So that's the entire circle, yeah? And we know that all of these three bits should add up to 0.4. So what do we have? That's going to tell us that 0.24 plus the 0.7, or 0.07, plus P will be 0.4. I'm going to write this as 40 though, because then we can think like, okay, got 24, yeah? Got 7 here, 31 altogether. Need 40, so I've got 9 left to go. So it should be 0.09. Again, big circle, lovely, jubbly. Oh, now we're told then A and B are independent. What does that tell us? That again, we want the intersection. And it's what you first learn about with probability when you're in like GCSE. If you were flipping a coin, you'd do heads times heads to get 2 of them, yeah? Because you can just times them together because the events are independent. One coin flip does not affect the second coin flip. And this is what we're trying to say. We want that to be true. So we can work out the intersection, i.e. the two events both happening, by just timesing them together, the chance of them individually happening. And this works 2 ways. If this thing is true, then they are independent. Because that's just like, it doesn't mean anything. It's just a name. Do you know what I mean? It's a description of this certain type of thing happening. So we want to fill in this equation then. The intersection of the two is going to be the only bit of A and B that were in both. Let's color in the A circle in red maybe, and the blue one in blue. Blue one in blue. The B circle in blue. The only bits in both then, that middle one, 0.24. And looking at the B then, it's all of those bits in it. So 0.24, well, we were told actually, weren't we? 0.4. That's for B. The A is a bit more complicated because we don't know all the bits. Let me rub these out. They're probably in the way actually. A bit easier without them. So the A circle then. Go away. How do we get rid of you? We do that. The A circle then is this bit, and this bit. So if we open some brackets up, we'll have that 0.24 and the 0.16. That makes a 0.4. And we're going to add on that Q that we have in there as well. Times that by the 0.4, and that should give us the 0.2. Lovely, jubbly. Now then we want to get Q. So don't expand the brackets. I think it's a bit easier if we just divide this across, yeah? 0.24, so 24 over 0.4, 40, should be, well, they're both multiples of 4. So let's divide them down. We're going to get 6 on 10. Divide that down, 3/5. Or I think 0.6 is what we want. So 0.6 equals 0.4 plus Q. So that's going to tell us that Q itself is equal to 0.2. Lovely, jubbly. Next bit then, we've got some conditional thing. Let's just circle that so it's easier to see. But we'll do it, say, we'll do it in blue, it's all right. Yeah, let's look at this one then. So conditional, that little notation means the probability. What's the chance of B not happening if C's already happened? So we know we're caring about the world where C occurs. What's the chance of B not happening inside that world? We have a formula for this. We want to find the intersection of the two events divided by C. So the given that event, like we know that C is going to happen in that world, then what's the chance of this happening? The tricky bit then, what's this thing? We want B intersection, not C. So duplicate that, take it with us. Over there you go, over here I come. That's what we're looking for. The way to do this then, intersection, we need to satisfy both of these. So it's the and condition, yeah? Both of them need to be true. So that's going to tell us that we want to get 2 ticks. We're going to go around, and every single one of these values, we could ask the question, are you inside C, and are you not inside B? That would work. We can have a little shortcut though. We know we need to tick both boxes, so we might as well just go and look at the C circle, because anything that's outside C is definitely not going to be allowed. So our only question then is, are P and Q not in B? So if we ask the question, are they not in B? It fails there and succeeds there, because this is not in B, but this is in B. So the only bit we need is going to be that R. All make sense? Hopefully so. Let's keep going then. Let's put these ticks on there so you can see that, yeah, the only section we get is that is R, the only bit with 2 ticks, yeah. I won't do, I'm going to confuse myself there. Let's just keep going. R's on the top, and like we said for C was R plus the plus P for the entire circle. P that we found earlier, where was that? 0.09. So it's R plus 0.09, and that equals what they told us above, the 0.64. Beautiful. This thing you can do, yeah. No issues doing that. So let's do it quickly. We'll times this across, and we'll need to expand these brackets with the 0.64. So timesing that together, what do I get? 0.64 times 0.09. I get a number of 0.0576. And that's going to equal, we need to add on as well, R times 0.64. 0.64, lots of R, and so that equal to R. Beautiful. Let's subtract everything away. Collect like terms. I'm going to have 0.36 lots of R equals 0.057 and a 6. And then divide by this 0.36. Whack that down there. Give it a division. What do we get if we do that sum? So divide that by 0.36. I get the lovely answer of 0.16. And that looks good to me. Let's check we are correct. So any of these, question number 1 needs to be on. Yep, they look good to me. 0.09, 0.09, 0.2. Yeah, 0.2 is good, and 0.16 is good as well. Lovely. Question 2. What have we got here? Some scatter graph. Describe the correlation. Well, it's going down, isn't it? So it's going to be negative. The variable on the x-axis is temperature. Okay. Temp measured in degrees. Use your large data set knowledge. What's on the y-axis? Well, it's going to either be rainfall or it's going to be pressure. And what are the units of those things? We have millimeters and we have hectopascals. That's just from the data set, yeah, just starting off top red. Stav then, on the next part, believes that there's a correlation between sunshine and humidity. He calculates the PMCC of these two variables for 30 days. He gets this value down here. Suggests a suitable test, or carry out a suitable test, to test his belief at 5%. State clearly your hypotheses and your critical value. Right. So hypothesis test, it's like a template. Same thing happens every time, yeah? We're going to have our null hypothesis. For correlation, that's always that there's no correlation. So i.e. rho is 0. The null, sometimes it'll specify. Up here, he believes that there is a correlation. And at no point has he said like which way you think it's going to be, yeah? So the null hypothesis, no, alternate hypothesis, is that this is equal, not equal to 0. Just there is a change. He hasn't suggested a direction for that change. Next thing then, we get the observation. That's that 37.7 number, yeah, or 377. So some R value is negative 0.377. And what we want to find then, so one way that we can view this is if we look at all the distributions, well, of the distribution of all the different possible correlations. So it's going to look something like this, kind of symmetrical. And the end down here will be -1, this end will be 1, and this will be 0 in the middle. We want to find some number, some R0, or we'll call it rho 0 maybe, that on the left-hand side of that is exactly 5% in general. But with it being rho, it's 2.5, yeah? So there's going to be some other number the other end. Same idea, we'll call this like rho 1. And the 5% has been split. So each one of these is 2.5%. And our goal then is to see basically whether the observation we have is inside this blue region or not inside this blue region. Because if we took just a load of samples, load of samples, and you pick 2 variables from, like loads and loads of variables, pick 2 of them, and compare the things on a scatter graph. Look at the correlation. This is just the display or distribution of all the ones we got. So our goal is to see the things that we're looking at right now, are they really unlikely just randomly? Or is there a big chance of them just happening in general? So that's our goal. What we have then to do is use our number and use the books on the left. We're told 5%. That gets split into 2.5s, yeah? So let's go to this column on the left. We have 0.025. And we have another column, sample size on the right. Our sample size was 30, yeah? So let's go down to the row with a 30 in sample size. And we wanted 2.5%. So the column with a 0.025, going down, what intersection point do we get there? We get a number of 0.3610. So that's our row 0.3610. This is the, I suppose they're the same value, so let's just call it like row 0 and row 0. But the one on the left is the negative. And then our goal is, yeah, where's our number? Well, we had 377, yeah? So that's in here somewhere. Negative, I know it's negative in it, but this graph is symmetrical, so like the negatives don't make any difference really. I mean, it's going to be the same thing if you're on the left or the right. But yeah, we're in the blue zone. That means we're a bit of a weirdo. There's very low chance of this happening. Less than a 2.5% chance of this just randomly happening. That's a bit odd, isn't it? So what we have is basically the idea that what we originally thought is odd. It's wrong. It's not correct. There is sufficient evidence to believe, or not to believe, to reject H0. That's the general idea. Why is, if we do the maths of it, we had the observation, the negative 0.377. If we look at the size of that number, so again, ignore the negatives, it's bigger than what we got from the book, the 0.361. Again, size of that, but negatives don't matter too much. So our observation is bigger than the kind of expected weirdness threshold value, what we get from the book. This is like 5% chance, or 2.5% chance, sorry, you have this correlation, just randomly. We were more extreme than that, more strange. So we should change our mind that nothing's going on, because this is just so unlikely that it randomly shouldn't happen. Always try and put this in context. So how I'd write this here, like there's sufficient evidence to suggest that there is a correlation between sunshine and humidity. I'd use that the full bits, do you mean? But yeah, that should be good. Don't say negative here because we haven't been investigating negative. We've been investigating just correlation in general. So we haven't proved negative. We've just proved that there's not one of these. Lovely. Hopefully that's all good. Part D then. What do we get? On a random day at Heathrow, the humidity was 97. Comment on the number of hours of sunshine you'd expect on that day. Give a reason. Well, we just showed negative correlation. Well, I suppose we did. Well, this was a negative side. So I suppose we showed we're in this gap where there is a negative correlation, really. You don't need to mention this bit. But in that regard, then, high humidity would be low hours of sunshine, yeah? Yeah. Lovely. See it from the graph too, innit? One goes up, one goes down. 97 is pretty high. So this should be quite low down. Lovely. Looks good to me. Let's keep going. What have we got now? 27 people completing a puzzle. Time taken for each of them was recorded. Here we've got some box and whisker plots. Find the range. Well, that's going to be the top value, Q4, and the bottom value, Q0. And what the difference between those two. What numbers are these? I get 7 on the left. That's 68. Looks 68 to me. So 68. Take away 7. I get 61 left over. Interquartile range. Same idea, but for not Q0 and Q4, but Q1 and Q3. So what are they? They are 14 and they are 25. 25 take 14 gives me 11. That's all nice and straightforward, yeah. For these now then, find the mean. So for the mean, we want to add them all up, divide by how many there are. So 607.5 divided by n, there's 27 of them in there. Let's do that quickly then. 607.5 divided by 27 is 22.5. Now the standard deviation. So sigma, we need to do the mean of the squares and then the square of the mean. writing out a bit more, we're going to have the sum of the squares over n, so the average square. Take away the square of the square of the mean, the thing we just found about that, 22.5, yeah. You can put that in there if you like. No, we'll leave that, and then we'll do, now this row, we have all the values, yeah. So this one is going to be 17623.25 over n, which was 27. Take away the thing we just found, 22.5, all squared. If you got the first part wrong, but then you did this net plot correct just with your wrong answer, you will still get all the marks, so don't worry too much. Let's plug this in, see what we get. That's too many fractions. 17623.25 over 27. We're going to take away 22.5, square that. We'll get quite a big number. What do we get? 146. Obviously, that's wrong, yeah? Look at that. Wrong, in it. What we've done wrong is we've not square rooted. So the formula we've done is for the variance. Standard deviation, square root, all of this stuff. So let's get rid of that number. Square root the answer we get. And it gives us an answer of 12.1. Which looks pretty good. Circle these as well. Always double check. The answer you get out, does it seem realistic? 140 odd? No. 12? Yes. So a little sanity check, always useful. What have we got now? Adam and Beth complete the puzzle in A minutes and B minutes respectively. A is bigger than B. So Beth's fast, Adam's slow. When the times are included with the date of the other 27 people, the median time increases. Okay, what does that tell us? Well, if you're going to drag the median up, let's think about A and B. We have B is bigger than A. So on a number line, the median can either sit on the left of B, in between the two, or on the right. If we're in between, one below, one above, we're not going to move the median, yeah? It's going to stay where it is. If we're like this, these two are smaller. So the median like moves to the left. If you're like lining all the numbers up, it moves to the left by one. So this will drag it down. But that side drags it up. So it moves towards them basically. If it's in the middle, it doesn't move obviously. But like whichever side it on moves towards these values. We want to increase it. So we need to drag it to the right. So we want to make sure our median is less than these values. Next with them, the mean doesn't change. So if you're if you're combining samples and you keep the mean the same, those two samples are the same, have to have the same mean. So these two values, I know it's a very small sample, just two of them, but we need their mean when we add them together and divide them by 2 to have the same mean that we had above. Doing that then, A plus B must equal, well, the mean above was 22.5 times by 2, we get 45. So two numbers, add up to 45, and they're both bigger than the median. What was the median? Let's go up here. 20, yeah, let's put that in. So we can come down here, fill that in. We know that this is going to equal to 20. And right then, two things we have now. Both numbers bigger than 20, add up to 45. What things are possible? Well, we can have 21, 24. Or we could have 22 and 23. These need to be ordered, so that's going to be B. The first one is smaller than A, the second one. That looks good to me. Lovely, jubbly. Right, next one. Suggest a possible value for A and... Oh, sorry, we've done that one, haven't we? Without carrying out any further calculations, explain why standard deviation of all 29 times will be lower. So what is standard deviation? It's not exactly this, but it's effectively, if we were to like look at all these things, you've got your mean somewhere, wherever our mean was it 22.5? In here somewhere. It's looking at the average distances away. It's not really. It's actually working out, like say you had 30. You are going to draw a big square and you work out the average size of all these squares, like all the values. I mean, how big are all these squares away from where we are? And we work at the average size of those and then square root it. Why do that and not just work out the average distance? It's just quicker on a computer. That's it. Only reason. So we do this way around. And what this represents then, yeah, roughly is average distance in terms of the units, like minutes here. We are away from the mean. So by adding in these two values, they're very close to the mean, yeah? So on average, our values are going to be closer to the mean. So that should reduce the standard deviation. So you say both of them are close to the mean, both close to mean. So that's going to imply that the standard deviation decreases. Decreases. On these sort of ones, these explain questions, let's just look at the mark scheme. Exactly what words have they used? Yeah, that's what the mark scheme is. It's a guide for how to answer the questions. So on these explain ones, just see what they want. You say this thing, I say this thing. I get the marks, we're both happy. Lovely. What does it say then? Both values will be less than one standard deviation from the mean, and so the standard deviation of all 29 values will be smaller. Looks good, yeah? Wonderful. It's only one mark, so like we've definitely ticked the box, haven't we? Like you understand that. Like they'll understand that you know what's going on because you said that. So number 4 then, we've got some distribution. Let's have a look what to do. So the one thing to think about, when we have a distribution, this fact is always true. If we add them all up, so every single value of little d, they add up to give us 1. So what that means, yeah, just add them all up. So we're going to have a tenth of k. I'm just taking out a factor of 1 on 10, yeah, k on 10. We've got 1 lot there. I've got half of them there. A third in that bit. There's a quarter and a fifth as well. And they should all add up to 1. So doing that, what is that big bracket going to be? 1 plus a half plus a third. 1 plus 1/2. And then let's get out of that fraction. Plus 1/3 plus 1 on 4 plus 1 on 5. We get the lovely answer of, this is going to be 137 on 60. So we have 137. Times that by the 10 on the bottom, 600. Lots of k is equal to 1. And get rid of that little dash in the middle. Pop. And now let's get k by itself. Let's times by this, well, divide by this weird fraction, yeah. 600 on 137. It's always nice when stuff pops out that looks the same, isn't it? That's good. The random variables d1 and d2 are independent and each have the same distribution as d. So independent is going to tell us a thing here. Whether we need it or not, different question. But generally, it tells us that the intersection, let's do it this way around. So d1 intersection d2 is the same as just times in their properties together, yeah. Same as what we had earlier on. And that's good. Whether we need it here, different question, but that's the fact that's always true. So it's probably worth writing down, like, if you see that thing. Here then, we want to find out what's the chance of them summing up to 80. How can we do that looking at these values? Well, the biggest we can get is 50. So we need at least 30 to get there. So we can either get 30 and 50, or we can get 40 and 40. Let's write that 5 a bit better. 5. One thing to think about though, we could also get 50 or 30. Like 50, 30. Do the other way around. They should have the same chance. D1 and D2 are identical. There's no difference in them. So these things, they have the same value, each one, like the chance of each one happening is the same. So you can really just think about the fact, oh, it's like 2 times that thing and just get rid of that bit. But that's good. So these are the possible cases to look at. And let's think about that then. So what is the chance of us having these values of 30? Let's do like each different rows of 40 and of 50. But we get them from above, don't we? We've got this k value. We've got k on 10, and we k on 30, 40, and 50. Nice and straightforward. I want to keep everything in terms of k. The actual value of k is not so nice, is it? So that's good. And the cases we want then, if we think about doing 30 and 50, we're just going to times them together. Because we want them both to happen, and they're independent. So we can just times them together. So what we're going to get? For this one, it's going to be k squared, yeah, on the top, over 30 times by 50 on the bottom. Very similar then in it for 40 and 40. We're going to have k squared over 40 squared. And like I said, we have 2 different ways that we can get to this. So we need to double that one, 2, and then add it all together, yeah? So we're going to have 2 times k squared on 30 times 50 plus k squared on 40 squared. This then is good. Let's add this all up. What do we get? So 2 times 1 over 30 times 50 plus 1 on 40 squared. We're going to get 47k squared on 24,000. Let's now plug in the value of k squared. So times in this by 600 over 137. Lots of k. Lots of k. Oh, all squared. We get, oh, not a very nice number. Should we get this number? No. Yes. Yes, we should. We should indeed. 0.03756. I'll always do 4 figs for stats. You don't need to. But I always say, like, if in doubt, do 4, basically. So the numbers here are, yeah, often going to be horrible. So I wouldn't doubt yourself, like, the numbers are so bad. Even though you naturally want to, don't you? But they will often just be horrendous. This is looking good. Last bit of this, then, is a little bit strange. What I'm going to do is just shrink this up out the way so we can still see everything. I will at some point, like when I post this, I will at some point like make this bigger and put the actual answers for part C on the next page. So what's going on? We now have a single observation, so not interested in D1 and D2 anymore. The value D is the common difference of an arithmetic sequence. The first 4 terms are measured in angles. The angles measured in degrees of a quadrilateral. So what do we know? The first 4 terms, A plus D, A plus 2D, A plus 3D, yeah? If we add those all up, because it's a quadrilateral, they will make 360. Let's collect some like terms. What do we get? We've got 4 A's and 10 lots of D. That gives me 360. And I will just half all that to make it a little bit easier. So 2A plus 5 lots of D equals 180. Lovely. Am I good there? No, sorry, not 5 D's. It's 6. It's 6 to begin with, and then it goes down to 3. 6 and then 3. There we go. We can have a little think about this. So we may as well make D positive. Why? Well, let's say we had 10, these went out to 360 for a sec. Let's say we had 10, 20, 30, 40. And that would start then, A is 10, D is 10, and we add up all the way. That's exactly the same as having A is 40, D is minus 10, and it's going down. So there's some relationship, because we have a fixed sum, there's some relationship between A and D, where like if you have, there's one value for A, and then like a negative value for D, and then the positive version of that is a different value of A. So we may as well just look at this side. I think that's a phrase of like without loss of generality. I'm still kind of relearning it. It's been a while since I've been there. Do you know what I mean? So I think that's what that's called. And like you can look at 2 different cases and just one of the cases works all the way around. Do you know what I mean? It doesn't change anything really. If I'm wrong there, someone correct me, but I think that's what it means. So doing that, what that tells us that the first term, A, is the smallest, which is nice. And we want to make sure that it's bigger than 50. Smallest angle, bigger than 50. So A is bigger than 50. That's good, yeah? That looks good to me. Let's write some things down then. If we know A is bigger than 50, 2A is bigger than 100. So these 3 D's, they can only go up most to 80. Any bigger, and we know we're definitely over 180, aren't we? Because these bits are at least 100, so they can't be more than 80. So that's less than 80. Divide that over them, what do we get? 80 on 3 is roughly 26, isn't it? 26 and a third, 2/3, something like that. Let's find out. 86 divided by 3. 26 and 2/3. Not that we need the 2/3 here, because the main bit's going to be that is smaller than 30. Because we can only be 10, 20, 30, 40, or 50. But that's less than 30. It's also, you want to say really like it's bigger. It's bigger than 20 as well, do you mean? But what the main goal of that really, like why we've done this, 10 then can either be 10, D, sorry, can either be 10 or 20, which looks good. So exact probability of doing that. What that really means is the probability that D is either 10 or 20. With it being or, add up the probabilities. So I should have K on 10 plus K on 20. If we do this, what is this? This is 2 over 20, yeah. So it's 3 over 20 altogether. 3K on 20. So if I take my K number, which was 600 on the 137, times it by 320, and it's going to give us a value of 90 on 137. As decimals, 0.6569. Does that look good to me? 90 on 137 is what they've got in the book. Beautiful. All sounds good. I'm just going to go to the toilet, and then we'll do, is it the last question? Yeah, last question, this one. Right then, last question, number 5. What have we got? Blah, blah, blah. Claims about the time, modeled by a normal distribution, mean of 10, deviation of 4. So, let's call that T, and it's going to be distributed normally with a mean of 10, standard deviation of 4, so 4 squared goes in there, make that a better 2. That's a good 2, isn't it? Oh, lovely. Right then, find the probability that time spent is more than 50 minutes. Probability T is more than 15. From this then, calculators, yeah. We will put in, just in case you're not sure on how to do these, we want the normal one. We can put in our stuff. The mean was 10. Standard deviation was 4. And we want to be above 15. Change that to above. What value do we get? 0. Oh, what have I done? Stretch you back out. 0.1056. Does that look good at the mark scheme? Does indeed. Lovely. They've rounded it to 106, but yeah, that's fine. Some patients complain that the mean time the doctor spends with them is more than 10 minutes. Takes a random sample of 20 patients, finds the mean time is 11.5. Okay, so on this one, yeah, it's a sample mean, not the one distribution itself. This is one person. When we get this value out, probably of one person taking more than 15 minutes. When we're doing a sample mean, we have the bar on the top to represent mean as always, distributed, and we're going to take the same mean that we had earlier, so the 10, but now that sigma squared was 4 squared, yeah? We divide that by the sample size, which was 20. The reason we do that, as you just add more people to the sample, so the average distance away from the mean should decrease, yeah? Add loads of them in, and you get closer to the average. It's a bit beyond the kind of course to think about why that happens all the time, like the maths of it, I think, but maybe not beyond what you can understand. So this is good. We want to change it via that then. Same idea though, probability that it's going to be, let's see, mean was 15. Okay, we're testing. We're testing. So, what do we get for our hypothesis test? 5% evidence to support their claim. More than 10 minutes. So, null hypothesis is going to be that the mean is equal to 10, because that's what we thought beforehand. The null hypothesis, she's thinking it's going to get bigger, more than 10 minutes. We have our alpha of 5%, significance level, 0.05. And we had a sample, like an observation of 11.5. So we want to find the chance that the sample mean that we got is bigger than the 11.5. So let's go to our calculator. Mean is still 10, that's good. What do we need for this? What do we need for this then? So let's move this out of the way a little bit. We have 4 squared over 16. What does that give us? 4 squared over 16. 4 squared over 20. So that's 16 over 20, 0.8, yeah? 0.8. We want to be bigger than 11.5. Bigger than 11.5. Let's press recalculate, and I get a number of 0.0304. That number is smaller than 0.05, the alpha value that we had from above. So what's that telling us? This means there's a 3% chance, roughly, 3.04% chance of, we have a normal average of 10 minutes. We've got 20 people doing it, and we've got their average of 11.5. There's a 3% chance of that being either 11.5 or more extreme, like bigger than, so like further away from the 10. Same idea as when we did this one earlier, wherever it was. Where have I drawn that little shape? Down here. Yeah, this same idea, do you mean? Same thing has happened, exactly the same thing. Just these numbers have slightly changed. This is now the 10, and the thickness of this has changed as well. But process is the same idea. Which group are we in? What we have observed is very unlikely to just randomly happen, so it changes our mind. Because again, we're in that same kind of rejection group, rejecting H0. What we actually observed was very unlikely. This is our observation, and this is our kind of threshold. Difference then, here we're talking about probabilities. In the other version, we were talking about the correlations. How you want to compare them is up to you. Whether you want to find probabilities and compare them that way, or find the actual values. We could have done the inverse normal here, taking the 7.5 in, and sorry, other way around. We're taking the 0.5% or the 5%, and we'll get at like what number that is, and compare these numbers and see, is it bigger than smaller or smaller than 11.5? And we would see, in this case, it's closer to the threshold will be closer to the mean. It'd be something like 11. So the observation was more extreme than the threshold. All good, yeah? Hope that makes sense. From here, then it's that statement at the end, yeah? Are we going to reject or accept? So from this one, we're going to reject H0. The observation we had a 3% chance of just happening. Our threshold for weirdness was 5%. 3% is more weird than 5%. So we reject our original thought. What we observed is too strange to think that we were originally right. I flipped a coin 10 times. I've got 9 heads. And I'm like, nah, man. I don't trust that coin's fair anymore. So I get rid of it. Beautiful. Next bit then. They're doing some more faff. What have we got? Claims that a dentist time, the time spent with a dentist during a routine appointment, multiplied by this distribution. So you spend twice as much time waiting than you do seeing them. Using this model, find the probability that a routine appointment takes less than 2 minutes. Okay, this is just calculate again, yeah. I will do them all on here just to show you. So make that so you can see. We have a mean of 5. This is going to be 3.5 squared. I don't think I can do squares in here. So what number actually is that? 3.5 squares. 12.25. I think you can do them on your calculator, can't you? So it's not an issue for you. And what we're looking for, less than 2 minutes. So below 2. Click the below button. Click calculate. We get a value of 0.4033. Make that better 3. Does that look good? No. What have I done wrong here? I didn't change my. That's standard deviation. Ignore me. This should actually be. Because my number's above, right then. Yep, sorry. My number up here, where we got this number, I thought my value in here should have been the variance. It should have actually been a standard deviation. So I've used a 16 and I should have used a. Yeah, what we've done 4 squared over 20 to get us 0.8. That is actually the variance. So I want to square root 0.8. That gives me a number of 0.8944. Oh, let's get rid of that 4 this done. 0.8944. Get rid of the 9. 0.8944. Is that right? Yeah, that's good. So just to clarify, this is sigma squared. So that tells us that sigma should be the square of that thing, yeah? 4 over root 20. If we do that, the number we get, just to double check, 4 over the square root of 20. Yep, 0.8944. So as I go through, the only thing that changes about what we've done is this actual number that we've got out of here. So if you do notice that you've made a mistake by doing that in the exam, you don't need to cross everything out. It's just this one from the observation. So we're going to go through, press recalculate. It needs to be now, this was above 11.5, yeah? So go back to the above one. The mean again was going to go back up to 10, sorry. Press calculate, and we get a different value then. So that 304 became 468. Thankfully, here, we were still on the same side, yeah? The comparison we did is still valid. It's the same comparison. So nothing else changes. It's just that actual value. Like, where does that come from? It's from the books. I think I wrote it over here. Yeah, that comes from this thing and it from the table. So that's all good. Sorry about that little slip up. I will try my best not to do them. If they're too big, I'll edit it out. But if it's just that, then I hope that's not too bad. So yeah, that changes what's going on here. Let's just re-clarify then. We want to use the mean of 5 and a standard deviation of 3.5. And we were looking for the phrasing of it. Find the probability that a routine appointment with a dentist takes less than 2 minutes. It's probability that t is less than 2. So going to be below 2. Yeah, we've got that on there. That's good. Plug that in. 0.1957. Does that match them? Does indeed. So blue, circle that. Big tick. Lovely. Down here then, conditional stuff. So we want to find the intersection on the top. So t is less than 2. Intersection, t is bigger than 0. And on the bottom then is, well, just the second one. So t is bigger than 0. That looks good. Thinking about the top then, how can we rewrite that? Well, we want to be less than 2 and bigger than 0. So less than 0 is less than the thing we're looking for, t, which is less than 2. Probability of that, and then probability of t being greater than 0 on the bottom. So we want the like between ranges, yeah? What's our lower bound? 0. What's our upper bound? 2. Plug that in. What do we get? 0.1191. If we do just above, do that from 0, what do we get? 92. So 0.9234. Let's do that sum, see what we get on the other side. 0.1191 over 0.9234. And we get a value of 0.12. What's 8979? There's loads of I things now, so it's 9, yeah, 90 if you're going 4 different places. Rounds up and up and up. Does that look good? Oh, it looks very good. Spot on. Next one then. Hence explain why this normal distribution may not be a good model for t. Well, yes. So one thing to spot. This thing. Let's put it in blue. Here. T bigger than 0. What are we actually talking about is the wait time at the dentist, yeah? I don't know any dentists that serve me before I arrive at the dentist. If I'm walking to the dentist, I don't have them like FaceTiming me like, "Oi, what's on? Teeth out in, yeah? I'll help." No, they wait until you get there checked in. So this is kind of like it should be 100%, shouldn't it? But it's actually 92%. So this dentist is claiming that like what 7 and 2/3% of the people get seen before they arrive. I don't think that's quite true. So why is that not a good model? Because people cannot be seen before they arrive. Yeah, makes sense. Big tick. I'll write this down. Cannot be seen before arriving. So that's it in terms of words. What does that mean? It's the same as saying really like t cannot. So t has to be bigger than or equal to 0, yeah? It probably has to be bigger than 0. Walk in, you just get seen straight away. Just walk in the dentist straight onto the seat, Jimmy. I'm here, boys, I'm ready. Right. What have we got for the next one? She believes she cannot do it in less than 2 minutes. Not surprised. She suggests that the health centre should use a refined model, only including bigger than 2 minutes. Yes. Find the median time for a routine appointment. Use this new model, given your answer correct to one single place. Okay. So what we want to find, we want the probability that the distribution of the times, some random value we get, some random person that comes in, we want to find a time. We can do greater than or less than. Let's find less than. Let's do greater than. It's a bit easier, I think, with what's going to happen. So that we are longer than that time, given that we are at least 2 minutes, yeah, so only considering the people that arrive after 2 or take longer than 2 minutes to wait. What time is the middle time? So what time is there half a chance that we take longer than it for? Exactly the same for a negative, yeah? Makes sense because it's just a half, yeah? What's the middle number? Only looking at the numbers that are bigger than 2, the times waiting that are bigger than 2. What's the middle number? What number have to be bigger than to be exactly half the numbers? Let's do the formula then for the left, the conditional. We want to be the intersection. So t is bigger than our time. I'm going to call this like t1 maybe. And intersection, we're bigger than 2. And over then, probably it's bigger than 2. Let's move that all left a little bit. So this is good. We know from the condition that we're bigger than 2. That's the only thing we're looking at, yeah? All the times bigger than 2. So this top row, where we want to be both bigger than our median time and bigger than 2, that's just the same as being bigger than the median time. Because we've kind of defined all times are bigger than 2. So by definition, it is also bigger than 2. Some of these, like, you think, oh, how are you going to know that? You just got to use a bit of common sense. There's not going to be like a definitive list of all the ways that these questions are going to be asked. Sometimes it's just a bit of common sense. We're only looking at times bigger than 2. So this one must be bigger than 2. So this thing is just the same as just itself. From here then, let's fill in all the values we have. Like I say, this is still equal to 0.5 from above. We're looking for that T1, so let's get that thing by itself. T is bigger than T1. And it's going to be a half at 0.5 of this probability. That's what we found above somewhere. Yeah, down here, this 1957. So it's a half of that number, 0.1957. As we do that then, what do we get? So 0.5 times 0.1957. We get 9785, but we're going to just round that up a little bit. So 0.0979 looks good to me. So again, what's that representing? We have some new distribution now. Well, yeah, we're capped at 2, so we can draw a line at 2. But then we've still got some, like, I don't know what shape it will be. It's going to go off and then go down to 0. And this whole thing, what is this? There's T in it. This whole thing will again have an error of 1 because it's a probability distribution. And we've basically found that we want to be bigger than some number, and it should have a very small, oh no, tell a lie, this has got the rest of it. So if we to draw it all out, it's going to stop here and be like 9%, yeah. But it's the same as then, it's like that number, if we flip all these bits around that were like invalid and like distribute them over the rest of the shape, what was splitting this into like 9% and 91% now splits it 50-50 because of all this kind of like excess bit that was invalid before being shared over. This number that was 9%, 91% is now the median number, so slap bang in the middle. This is looking good. Double check I'm right. I don't think I'm right. What have I done wrong? T bigger than 2. T bigger than 2. Sorry, that's T less than 2. So it should have been 1 minus this thing. 1 minus that. Sorry about that. Move that over a little bit. 1 minus that. 1 minus that number. So let's just slightly change the things we did. 1, take away that. What do I get? So it's not 97 stuff. It's going to be 4022. The way I explain this is the same. The numbers have changed, obviously. It's now going to be like it was 40% and 60%, and now it's 50-50. But same explanation. This is good then. So that is the probability for us on our original one to be bigger than 40. So or bigger than 40, having like 40% on this side. So what we want to do, we want to think about doing the inverse normal. So let's go and get our inverse normal calculator. And we know we want to be, we have a mean. I'm always going to do the inverse normal, the inverse standard normal. So we have an area we want to find is 4022. That's 0.4022. And let's just plug that in. Or should we? No, I think we'll do it the way that you do it. So we can just do the mean and the standard deviation here. So what was our mean? Our mean is still 10. Our standard deviation is still 3.5. Oh, sorry, our mean is 5. Doing that then, what number need to be above 5.8668? So yeah, from the calculator, that's going to tell us that T1 is equal to 5.8668. Lovely jubbly. Is that the last one? Yes, it is. I'm going to take a little break while this one edits and loads and stuff, do you know what I mean, and processes. The other ones, I'm just going to keep doing this now. I don't know what time I'll finish whenever I get tired and bored. Probably, like, I'm thinking in my head, like 2 a.m. is when I'm going to stop. So yeah, enjoy. How many you want, I don't know how many I do today. I'm going to do at least 4, hopefully if not more than that. But the rest of them I will just do tomorrow. So by the time you go to bed tomorrow or wake up on Tuesday, they'll all be out, yeah. Happy days. Thank you very much. Enjoy. See you later.